Okay, on to the actual exercise, which is to show that if X is inductive, then this set, the set of all elements in X that are subsets of X, is also an inductive set. From this, we should be able to infer that n is transitive, and this fact that every number is the set of all numbers less than it. Okay. We would like to show that, first of all, I'm going to use the notation x prime to denote this set, which we will refer to often. And we want to show that x prime is inductive, so we want to show that the empty set is in x prime, and if anything is in x prime, then it plus 1 is also in x prime. Okay, how do we show that the empty set is in x prime? We need to show first that the empty set is in x. After all, x prime is just this set. We need to show so that something's in it, we need to show it's in x, and we need to show that it is a subset of x. Okay, how do we know that the empty set is in X? Well, X is inductive. Every inductive set has the empty set. That much is done. The second fact is a generic fact. The empty set is a subset of every set, so that requires no further proof. Okay. Next, we want to show that if A is in X prime, then A plus 1 is in X prime. How do we show that assuming A is in X prime, how do we show that A plus 1 is in X prime? We have to show that A plus 1 is in X, and also that A plus 1 is a subset of X. Okay, how do we see that A plus 1 is in X? Well, we know that A is in X prime, therefore X prime being a subset of X, we know that A is in X. Since X is inductive, A plus 1 is in X, and that's what we wanted to show. Okay, next, how do we show that A plus 1 is a subset of X? Well, I'll use the standard subset style proof. I will take an arbitrary element out of A plus 1 and argue that it must be in X. Well, if an arbitrary element B is selected out of A plus 1, which you must remember is equal to A union set of A, this means that B is either in A or it is in this set. Now, if it's in this set, that just means that B is equal to A. So really, B being an element of A plus 1 means that B is either in A or it is A. Okay. If B is in A, but we have already established that A is in X prime, and being in X prime means that A is a subset of X. That's just the definition of X prime, is anything that is in it is a subset of X. Then B being an element of A, and A a subset of X, implies that B is in X, which is exactly what we wanted. We have already argued for the latter case that that A is itself in X. So if B is equal to A, then B is in X. So that is also done. And in fact, that concludes the whole proof. So now we would like to show that from this we can infer that n is transitive. Well, first I would like to point out that it's inductive. And we just proved a fact about all inductive sets, right? So for this inductive set, we could also argue that this is inductive, right? The set of all elements that are subsets we showed is inductive if you are selecting out of an inductive set. That was what we just proved. Now, the other point is that n is the smallest inductive set. So if this is inductive and n is the smallest inductive set, n must be a subset of it. Okay. From here, the proof is very fast. I want to show that n is transitive at this point. How do I show that n is transitive? I must select an arbitrary element and show that it is a subset. Well, if I pick an arbitrary element out of n, which must be an element out of this set, therefore it is a subset, which is exactly what transitive means. Okay. To finish off, we would like to show that every number in n is equal to the set of all numbers less than it. The proof is very trivial. If you pick an arbitrary, and to show that these two sets are equal, I'll, pick an arbitrary element out of M and show that it's in this set. That'll establish the, leftward subset relation, and then you could do the reverse argument, picking an arbitrary element out of here and showing that it must be in M, and then you'd get that they're subsets of each other, and therefore they must be equal. Okay. but I'll just do it in one direction. It's very trivial in both directions, actually. But here, let's pick an arbitrary element out of M, call it A. Well, the inclusion relation just is the same thing as one number being less than the other number, and therefore A satisfies the conditions for being in this set. The opposite direction is just as trivial, so there you have it. That is the solution.